If you look at your handout, you're going to see that the problems are broken down into 4 different categories. This video is going to go over 3 of those 4 categories. So the first type of problem that we're going to go over is using energy to solve problems that are projectiles. So in this example, a projectile is launched at 30 degrees above the horizontal at a speed of 25 meters per second. How high does the projectile go from its initial launch point, and what is the speed of the projectile if it was launched from a height of 30 meters? Now, if we were going to do this back earlier this year, right, we'd have to take our 30 degrees above the horizontal and 25 meters per second. We would have to split it into its x and y components, right, because if it's moving at 25 meters per second at this angle of 30 degrees above the horizontal, we would need to know the Vx and the Vy initial, right? Well, to find the Vx, remember in the x direction, it's always a constant speed. So cosine of 30 degrees would equal Vx over that initial velocity, and sine of 30 degrees, right, would be the Vy initial over V initial. Well, with energy, it's a little bit easier because once we got those numbers, we'd have to figure out the time and final velocity. We'd have to do all sorts of crazy work. So I think energy makes it a little bit easier to handle these problems. So let's look back at the x velocity, right? So cosine 30 degrees is Vx over V initial. Well, another way we could look at it is, right, Vx equals VO cosine 30. And we did that last semester. So if we want to answer part A, how high does the projectile go from its initial launch point? Well, from its initial launch point, let's just assume that it's at a height of 0. I know it says that it's launched from a height of 30 meters, but for part A, we'll just say the height of 0 is the top of the building. So if it's launched from the top of the building that has no height, then that means that the only type of energy it has is kinetic energy, right? 1/2 mv squared. Well, energy is a scalar quantity, so we don't need to separate it in that 25 meters per second into x and y components because energy is scalar. Well, at the top of the path, right, there's gravitational potential energy because it's now higher than it was before. And don't forget, it's now moving in the x direction only at the very top of the path. So your energy at the top is gravitational and kinetic because of that x velocity. So again, I've already got the red marks in there that mass cancels out. If we had the mass, we could put it in. In this case, it doesn't give us the mass and we don't need it. So plugging in our numbers, we're at the initial velocity. Even though it was diagonal, I just punched in the 25 because energy is scalar. Right? I have the x velocity we said over here is VO cosine 30. So 25 is the VO. So 25 cosine 30 is your x velocity. Don't forget to square it. And when you start plugging in your calculator, right, 1/2 25 squared is 312.5. The 1/2 25 cosine 30 squared is 234.375. Solve for h, and you get it goes 7.81 meters. To me, that's a lot faster than doing it the other way that we had done it before. I just think energy is a little easier. Let's move on to B. What is the speed of the projectile if it was launched from a height of 30 meters? Well, if it's launched from a height of 30 meters, then we now initially have this kinetic energy and some gravitational energy because it's 30 meters off the ground. Now for part B, it says, what is the speed of the projectile? Well, it doesn't say what's the final velocity in the y direction or what's the final velocity in the x direction. It just asks what speed is it going. It's moving diagonally down and to the right. Well, we can find that speed pretty easy using energy. Again, the masses would cancel out, so I've left them out of this equation down here at the bottom. Um, we have our 25 as our initial velocity again. Its initial height is 30. Because it's right before it hits the ground, there's no gravitational potential energy over here. And so solving for our VF, right, again, our 1/2 25 squared is 312.5. Our initial gravitational, right, 10 times 30 is 300. And then we've got the 1/2 VF squared. Now, this 312 and this 300, this is not in joules because we've canceled out the mass, right? But it still can be used to solve for that velocity. So the final velocity, or the final speed, right before it hits the ground, is 35 meters per second. And yeah, it's at an angle, but because it says speed, we don't need to find that angle. So it's easy enough. Let's move on to the next problem. Okay, this is an example problem where we're using work. Now, we've used work in previous problems, but you're going to see that this one is a little bit different than what we were doing in the past. So we have a 12-kilogram box is being pushed across the floor, assume it's a horizontal floor, and it's pushed with a force of 6 newtons at an angle of 30 degrees below the horizontal. Part A, how much work is done by the pushing force, it should say, if the box moves 8 meters, and B, if the frictional force is 3 newtons, how much energy was dissipated over the 8 meters, and part C, if the box started from rest, how fast is it moving at 8 meters? So, work we know is force times distance. Well, I'm sure you don't remember, but when we initially went over it, I said a very important thing with work is that the force and the distance have to be in the exact same direction. So if this box is only moving horizontally, then we only need the force that's making it move horizontally. That 6 newtons is at 30 degrees below the horizontal. So we don't need all of that 6 newtons. We can only use the x component of that force. Well, if you look at an equation sheet for the AP Physics test, it would look something like that, where you have FR cosine theta. The R is just the D, right? That's something they do. Now, this FR cosine theta, the way that it's written, it doesn't really make a whole lot of sense, but if you look at it this way, hopefully that makes a little bit more sense, right? If we're looking for F cosine theta times R, well, that blue line represents the force that's in the x direction, and the black line represents our pushing force of 6 newtons at an angle of 30 degrees below the horizontal. How would you find this x component? It's adjacent to the angle, therefore you'd use cosine. So similar to our other example, right? F cosine theta would be the force in the x direction. Right? So F cosine theta is Fx, and that's what we need, right? We need Fx times d. So this F cosine theta gets us Fx, and now we can put in our distance of 8 meters. So using that equation, right, we have a force of 6, a distance of 8, or in the equation it's r, and cosine 30. Again, the 6 and cosine 30 is getting us the x component of that pushing force. So 6 times 8 times cosine 30 is 41.57 joules. So the pushing force, or whoever was pushing, did 41.57 joules of work. The rest of it really is pretty straightforward. So part B, if the frictional force is 3 newtons, how much energy is dissipated? Well, now, if you look at that equation again, FR cosine theta, well, now we're not at an angle. That 3 Newton force is acting horizontally only, which means cosine theta, it's an angle of 0. And this is why our equation FD was working before. If you put in your distance of your force of 3, your distance of 8, and cosine 0, well, what is cosine 0? Plug that in your calculator. Cosine 0 is 1. So 3 times 8 times 1 gives you the work for friction. So essentially, if the force and the distance are in the same direction, we just leave this out We don't include it because there's no need for it. It equals 1 anyways. And the last part, part C, if the box started from rest, how fast is it moving at 8 meters? If it starts from rest, it has no initial energy. The person is going to put in 41.57 joules. The friction, right, is negative work. It's going to take 24 joules out of the system, leaving it with some kinetic energy. So we know 41.57 is put in, 24 is taken out. It has a mass of 12. Solving for that velocity, you get 1.71 meters per second. And that's how fast the box will be moving after 8 meters. Okay, moving on to the final type of example problem. This is over a pendulum. So we have this situation over here to the right. There is a 2 kilogram metal ball, right? It's attached to a string that is 0.8 meters long. And it says that it is pulled back so it makes a 12-degree angle to the vertical. Now, if this ball was released, it would swing back and forth and back and forth and back and forth. So the question is, how fast will it be moving when it gets to this location right here? Right? When this thing swings down to here and it's right here, how fast is it going to be moving? This one's a little bit more involved. So again, taking that picture that's before, right? It's released. It's sitting there at a velocity of 0. The length of this string is 0.8. Well, we can figure out, because we're going to use energy, what we need to do is we need to figure out how high this object is from one position to the other. Well, as you can see over here, if it swings down, it's going to get lower. So what we really need is we need the height from here to here. And if we make this height here a height of 0, then this will be our h for our MGH. So going through that process, if we know that this is at a 12-degree angle and this length is 0.8, right, similar to before, that our L1, or the length of our string in our string for our first situation, right, we're going to kind of looking at height essentially, is adjacent to the 12 degrees, so cosine theta would equal what I've labeled L1 over L, the hypotenuse, right? So that means that L1 is equal to 0.8, the length of the string, times cosine 12, which comes out to be 0.7825 meters. Right, so the length from here to here is 0.7825 meters. Looking at the point where it's at its lowest point, right? This is the point that we want to know how fast it's going at. It's going to be a little bit lower now because the string is straight down. So if this length was 0.7825 meters and the length when it's straight down is 0.8 meters, the difference in height, again, we're saying that at this lowest point, we're going to say it's a height of 0. The difference in height here is 0.8 minus 0.7825, right? So there's a difference in height from the initial to the lowest point of 0.0175 meters. After all that work, now we're finally ready to go and make our energy equation. So initially, if it starts with this velocity of 0, it only has gravitational potential energy. And at the bottom, if it's at a height of 0, it only has kinetic energy. So plugging in our numbers, and we could cross the mass out if we wanted to, right? Because it's in both sides. I put it in on this one. So 2 times 10 times our initial height, right? So that's this red line over here. That from here to here, right? Or this difference in height is 0.0175 meters. And then at the bottom, if it's at a height of 0, it's all kinetic. Solving for that velocity, you get 0.59 meters per second. Hopefully these will be a good guide for you to work on the problems on pendulums, the problems on work where forces are pushing at an angle, and using energy with projectiles.